So in polynomial regression, we no need to converting nonlinear data into linear data. Directly to the data only we are applying the this regression model. Regression model. How we are applying this regression model to nonlinear data means by simply adding the polynomial terms to which one independent variable. That means we are having the polynomial degree, maybe some degree 2 or degree 3 or degree 4. Like that we are having the polynomial degree value to the independent variable. From that we are getting the equation, or from that we are getting the polynomial model to the given data set. So in the later slides we clearly understand. So now let us see how this polynomial regression works. Okay, so the equation for polynomial regression is y equal to beta naught plus beta 1x plus beta 2x square and so on beta n xn. Let us see here what is x here. The x is a independent variable. We have the single independent variable, but here we are having the the terms may be x degree 1 here x square and x power n. That means we are adding some degree to the independent variable. This is the equation for polynomial regression. Okay, so by adding the degree to the independent variable, okay, we may also get the final model to which one polynomial regression. So how it will works we can see later. Okay, so the low degree polynomial like quadratic or cubic often captures the basic nonlinear patterns. High degree, if you are trying to take the high degree for equation of a polynomial, okay, the high degree value may give the complex model. That complex model may leads to the problem called the overfitting. Okay, so to balance that one we are using some bias variance trade-off that we'll be discussing later. Okay, so this is the equation for polynomial regression. Okay, simply we are adding some degree to the independent variable. From that we are getting the polynomial regression equation. Let us say, for example, if we are having the two independent variables, how we are writing the polynomial equation? For example, we are having the two independent variable x1 comma x2. For that case, we are writing the equation like this: beta naught, beta 1 x1, beta 2 x2, beta 3 x1 square, beta 4 x2 square, beta 5 x1 x2. All the combinations of x1 x2, we are adding the which one? Some coefficients: beta naught, beta 1, beta 2, beta 3, beta 4, beta 5, and then we are having some error value. Okay, that is, this is the polynomial regression equation for two independent variables. So now that means what we are observing here is the polynomial regression equation becomes a complex if the number of independent features are more. That is also one of the maybe drawback of the which one polynomial regression. Now let us try to understanding how this polynomial regression equation. Here I am taking the degree equal to 2. Degree equal to 2. Here I am taking the the data set with 5 features. Okay, the independent variable is a speed. A dependent variable or the target variable is stopping distance. For example, I want to predict, okay, what is the stopping distance, okay, if we are moving the particular car with some speed. Okay, so the stopping distance is depend upon the speed of the vehicle. Okay, now for this case how we are applying the polynomial equation, okay, with the degree 2. Here we are having how many independent variable? Only one independent variable. First is we are define the model or write the equation for given based on the data set. In our data set, we are having only one independent variable x, and degree is how much? The degree value here I am choosing is 2. Clear? That's why if for degree equal to means this is the polynomial equation. Y equal to beta naught plus beta 1x plus beta 2x square plus epsilon. We know that y is the dependent variable, x is the x or is independent variable. Okay, beta naught is the intercept. Clear? beta 1, beta 2, maybe beta 1 is linear coefficient, beta is the quadratic coefficient. Okay, if I add the degree 3, beta 3 x cube. Okay, that may be some cubic coefficient. Likewise, the value of based upon the degree value, the equation may be changing. Here I am taking the degree equal to 2. That's why we are getting the equation like this. So now from this, what we have to do is, okay, so now we have to set up the model with matrix notation. Okay, so now y equal to, here we are set up the equation like this, x dot beta, what's called as x dot beta plus epsilon. Okay, we are forgetting about this epsilon value. We have to mainly focusing on y equals to x into beta naught, x into beta. Here, what is y here? Y is the vector, okay, of y values. We are having 5 values. Those 5 values have to make it as which one? One vector. And x is the one matrix. X is the matrix with column. Okay. Here, what is the value of degree in our example? Degree is 2. That's why we are getting the beta naught is 1 and linear coefficient is x and quadratic coefficient is with x square. That's why like this we have to representing the matrix with 1 comma x1 comma what's called as x square. The first column is all ones for which one? Beta naught. So x1, x and x square values are changing. Okay, in the coming next slide we will understand how we represent this matrix. And beta is one more vector of coefficient with beta naught, beta 1, beta 2. So the equation for polynomial regression we have to simplify it as y equal to capital X into beta. Y is one vector with values of what is called as target variable values. Beta is one vector with all the coefficient. X is the one matrix that can be represented based upon the degree. Okay, this is how we are calculating the beta naught, beta 1, beta 2. What are the vector for beta? The vector for beta is beta naught, comma, beta 1, comma, beta 2. Now, the equation for beta again we have defined as, here I am using the to estimate the coefficients. If to estimate to calculate the values of beta naught, beta 1, beta 2, here I am using the method called as ordinary least squares method, OLS method. Okay, so from that OLS method we may getting the lowest error. That's why I am using the ordinary least square method. This is the equation for beta, x transpose x all to the power of inverse into x transpose into y. Then we are getting one vector. That vector is given as beta, values of beta. Okay, let's take this is the equation. This is a what's called the simple scenario how to solving the polynomial regression. Okay, problem. Okay, with degree equal to how much? 2. This is the data set. We already seen this data set. Clear? Now what is x here? X is matrix with a column 1 comma x comma x square. Clear? I already discussed this one. What is the first one? First is 1. What is x? 10. X square is 100. Next is 1. X is 20. 20 square 400. Next x is 30. 30 square 900. Like this we have to define the matrix x. Y is the vector with which variable? Target variable. What are the values of target variable? 9, 30, 60, 100, 150. Like this we are defining the y. We know the x, we know the y. Simply we are substituting into which one? This beta equation. Okay. Then we are, if we are knowing this matrix multiplications, transpose, inverse, all those things, we can solve this equation. First we have to find the transpose of x that can multiply with x. To whole thing we have to find in the inverse. that can be multiplied with X transpose, that can be multiplied with Y, then we are getting the matrix like this: 5 comma minus 1.2 comma some 0.1, like this we are getting the matrix. Okay, now in this the beta naught is 5, the beta 1 is minus 1.2, the beta 2 is 0.1. Now simply we are substituting in the polynomial polynomial regression equation: y equal to beta naught plus beta 1x plus beta 2x square. We are substituting the beta naught value, beta 1 value, beta 2 value. Clear? Then this is the final model equation to the given data set. By using this model equation, we are predicting the value for the new data point. Let us, for example, if I am giving the data point x value is 35. So what is the stopping distance if I am giving the new data value x equal 35? Simply we are substituting the x equal to 35 to that equation. We are getting the value of 5. That may be a value 85.5 is a stopping distance to the given value 35. Okay, likewise we are predicting the value to the given new data point with the help of which one? Polynomial regression. Clear? So what will happen, and what is the best value for the polynomial regression degree value? Let's check if these are all the blue points are the actual data points. If we are taking the degree equal to 1, we are getting the line like this. We are getting a line like this. So if you are observing this line, majority of the points are not nearer to this line or does not cover this line. If taken as degree 2, if degree equal to 2, okay, some of the points are within this curve and some of the points are far away to this curve. Clear? If degree equal 300, let's see, we are getting the curve like this. Okay, getting the like this. So from this curve, maybe it covers all the data points. It cover the all the data points. That means if degree equal to, if you're choosing 300, it may gives the minimum error compared degree equal to 2. But if is more, let's see this curve, if for degree equal 300, it is a more complicated curve. So if you are increasing the value of polynomial degree, we may getting the best training error, but that may be failed in the new data point. That means higher degree value may be suffered with the overfitting problem. Okay, that's why we are trying to choose the value equal to 2 only, even though it may give the little bit of more error compared to degree equal to 300. We are choosing 2 only. Why? Because if you are choosing the degree value equal to 300, the model may becomes a complex. If the model becomes a complex, then that model may be suffered with the overfitting. That's why here we are choosing the value equal to 2. Okay, so that is briefly about the model. Also, how we are solving that overfitting, all those things we will discuss in the later. Okay, that is about the polynomial regression.